And now you know you're being recorded. So welcome. It's very exciting to meet with you and go through just some basic thermochemistry. I just pulled some example questions I thought we could work through. People will be coming and going from our meeting as best they can to meet their own schedules. Before I start, I do have the chat open, or you can open your mic and just ask any general questions or comments of how things are going for you. I'm just gonna be quiet for a minute and see if anybody has a general question for the crowd about the class or how things are running. Anything at all for the good of the class. You can type it in the chat or you can open your mic. Let me give you a minute to do that. Got a good crowd, so feel free to type or to just use your microphone. Ashley, I see your face. Thank you for turning your camera on. Hey, Ryan, good to see you. Looks like we're still coming together and just kind of putting it up. And if you do have a general question, feel free to type it into the chat, and I'll do my best to keep an eye on it. I'm going to begin by sharing my screen. So let's see if I can get that accomplished. Reminding you that if you're just joining, we are being recorded just so I can share the recording with those who could not attend. And I wanted you to just welcome you. It's great to meet you. If you are first time meeting me, Mrs. Hanson, I've been in our chemistry department for a few years now. But as I mentioned in my intro video, it's probably my 34th year teaching general chemistry. So, still in a modality that we're all getting used to. So bless you for coming to our review session. So one of the things I wanted to just comment on is, how are your quizzes and your tests arranged to kind of give you an idea of what to expect. If you've not yet opened your first attempt quiz, or maybe you have taken one attempt, just to clarify what to expect when you open them. So let's say my thermochemistry, and I'll say the objectives or the number of sections. I'm going to say that there's 4 main sections from our chapter. So we did a little introduction to what thermochemistry is, the first law of thermodynamics, kind of did some basic vocabulary introduction with endothermic, exothermic, talked about in terms of Q and delta H. So I called that kind of my first major topic, kind of more conceptual, vocabulary-driven concepts. And what I did was then to create a test bank related to that very specific topic. And there's probably 25 to 30 questions from that first section. In the next section, I did some basic calorimetry, some MC delta T with a coffee cup calorimeter. In a next section, I kind of focused on stoichiometry and thermodynamics, to where you're looking at balanced equations and solving how much heat comes out from a specific amount of reactant and so forth. And then kind of a last major topic, we looked at Hess's law and its applications of being a state function independent of pathway, and kind of those little puzzle pieces, I call them, when we look at how do we put elementary reactions together and create a big target. And then more specifically, even thinking of that product minus reactants equation kind of at the end of our presentation. So with those 4 main sections, I grouped the test questions into one of those 4 categories, and then each one of those will get randomly pulled to create your quiz. I do this to ensure that you get presentation, a question that is related to each of those 4 sections, and that the quizzes yet are still random, so you're not getting the exact same questions as your neighbor is. So the content questions will be parallel. I want to make sure that you have a sample question from each of the major topics. And, instead of having 100 questions and randomly pulling 10 with no guarantee you'll see one of each topic, this is my way of ensuring that you are covering the content. Now, I also wanted to comment on why I'm giving practice tests, these little practice quizzes before the main event. And I just think the more you see the style and rigor of the actual test questions before you sit down and take the test, the less anxiety you have, the more prepared you are. So I just think of those as little dress rehearsals before the main event. It gives you a good taste of the test bank that you'll be expected to master. And of course, the test then is coming from the same bank as the quizzes, and you'll answer 25 questions this time. As our modules go forward, I want to make sure you know that there is a little section there of making sure that you have some distributive practice as well. So for instance, the next module, there'll be a few questions from the first module. By module 3, you'll have a few questions from module 2 and module 1. Keep appearing integrated, just to keep you fresh with all content. Okay, so enough rambling there. I just wanted to make sure you knew how the quizzes were kind of designed. I make sure that we're all getting a representation of every topic we've covered. All right. Well, cool. So, hey, why don't we jump in? I'm going to share my questions kind of one at a time. And what I'm able to do then is give you a moment if you wanted to jot down the question and solve it with me, but kind of just strategize with you. These are actual snapshot quiz questions. Sometimes I include the multiple choice if I need them. Sometimes I just eliminate them so we can work it out. So this particular quiz question asks us to consider enthalpy change and use a little bit of stoichiometry along the way. So I'm going to read the first sentence with you and kind of figure out what that means. It says the standard molar enthalpy of formation of NH3 gas, and it gives me a number of 45.9. So I really want to highlight this term, molar enthalpy of formation, so we clearly understand that definition. The heats of formation, molar enthalpy of formation, the key word here, of course, I'm forming a compound from its elements in its natural state. So I'm going to point at NH3 within the gaseous phase, and then consider what are the elements that's building that compound. Well, the 2 elements building it obviously are the nitrogen and the hydrogen, who in nature exist as diatomic molecules. So we have N2 plus H2 in their gaseous form, which is how we find them in nature, pointing at ammonia. And we can see that it's not yet balanced, but what's critical for the definition of molar enthalpy is that the ammonia has a 1 for a coefficient. But see, that's the definition of the formation. It's how much energy is needed to build 1 mole of the compound, which they're telling us here, the delta H of this reaction is negative 45.9 kilojoules for every 1 mole. Now, let's think about balancing. On the right side, I have just 1 nitrogen. I know on the left side, it's a diatomic, so it's N2, but I can just simply put a fraction there and be fine. I can put N2 with a coefficient of 1/2. 1/2 of N2 is 1 nitrogen. And then we could do the same thing here. We could write 3/2 nitrogen, producing 1 mole of ammonia. It's okay to have those fractions there because the heats of formation for any element in its natural state we know is 0. So it's not something that is really just bookkeeping. But I also wanted to comment, if this bothers you with fractions for coefficients, then all that means is if N2 reacts with 3H2 to form 2 ammonias, which is very much what we're used to seeing for the Haber process of the production of ammonia, keep in mind that this delta H of reaction then would have to be 2 times negative 45.9, simply because we're making 2 moles worth of it. So I'm just kind of stressing that first sentence. That value of 45.9 is for 1 mole of ammonia. So I like to just use fractions, but it's more of a preference for you. Now here's what we're given. I have 9.51 grams of nitrogen, and I have 1.96 grams of hydrogen. So here is our given quantities. What we want to know, and this is just really our stoichiometry part, what is it we want? We want to know the heat. So we want the delta H. This turns into really nothing more than a limiting reagent problem, right? I'm given the quantity of both reactants and want to know the maximum yield. For me, when I teach the stoichiometry part in Gen Chem 1, I always say, again, it's so many correct pathways to the right answer, but perhaps the easiest way is to just solve 2 separate problems and then realize that the maximum yield is just going to be the smaller of the 2 answers. So in other words, I would start this by saying I have 9.51 grams of N2 times, and I know that the molar mass for N2 is 28 grams. I can get my grams to cancel. And then in the next conversion, I just think about what I want over given as that stoichiometric ratio. I know that there are 45.9 kilojoules for every 1/2 moles nitrogen. So I'm just grabbing that coefficient. That's called your stoichiometric ratio, want over given. So in the first conversion, we change grams to moles. In the next conversion, we cancel moles. I should put that unit there. That's a mole unit. And canceling the moles gets us to kJ. So on my calculator, 9.51 divide by 28 times negative 45.9 divide by 0.5. So my first answer, one possible correct choice there, is negative 31.18. But I was given a second quantity, right? I was given the hydrogen as well, the 1.96. The same strategy here says, I know that in 1 mole of hydrogen, there's 2 grams. So that's just dividing by molar mass to convert grams to moles. And in its stoichiometric ratio of want over given, we have negative 45.9 kilojoules, and its coefficient was 3/2 mole H2. So with this example, 1.96 over 2, whoops, and then times negative 45.9 divided by 3/2. And this answer on my calculator reads negative 29.376. So when I compare the nitrogen value to the hydrogen value, what is the maximum amount of heat that will be yielded is smaller of the 2 answers. That's your limiting reagent, and therefore your excess reagent with nitrogen. So I'm only allowed to produce as much heat as the limiting reagent allowed. So with this, the reason I selected this question, a couple of things to kind of digest. I wanted to emphasize, what does it mean to have the molar heat of formation? You've got to make sure this coefficient is a 1. do whatever it takes to balance the equation to make that a 1. And then I was able to kind of sprinkle in some stoichiometry review looking at a limiting reagent problem. Now I'm going to be quiet and give you a moment to digest and see if you have a question before we move on. If you do have a question, I'll just look for it in the chat, or you can certainly open your mic. But I'm going to pause and give you a moment to digest, see if anything pops to your mind.
Hi. You said the hydrogen was the limiting reagent and the nitrogen was the excess what?
So I'm going to bring us back, and let me just kind of clarify. Those are terms that were taught back in Gen Chem 1, right, in your stoichiometry. And the term limiting reagent is the one that runs out first. The excess reagent is the one you have extra of. So I can kind of clarify that in terms of, just maybe another example. When I wrote N2 plus 3 H2s give me 2 ammonias. The perfect balanced equation says I need 1 mole of nitrogen to react with 3 moles of hydrogen. If I run this recipe with the exact most perfect ratio, I wouldn't have a limiting or excess reagent. Anytime I run this recipe using other mole ratios, I do set up those 2 terms. One of them will be called limiting. It's too small, if you will. And the other is the excess reagent. It's the one you have too much of in comparison of the 1 to 3 mole ratio. So just thinking about 9.51 grams, and I have to keep scrolling up so I forget. This was 1.96. Think about what that means in terms of mole. I'm going to do 9.51 divided by 28, and I'm doing that because that's its molar mass. It's 0.3, I'll say 0.34 moles. And here I have 1.96 over 2. That's me converting to moles. All right. Now this is the key. The perfect ratio is 1 to 3. Even though hydrogen is bigger, it's a bigger number, is it 3 times bigger than 0.34? When I hit that 0.34 times 3, that answer is 1.02 moles. So you can see, to consume all of the nitrogen, I need 1.02 moles, but I only have 0.98 moles. It's not quite enough, is it? So it's going to run out before the nitrogen is consumed. That's our definition of a limiting reagent. We ran this equation without using the perfect mole ratio of 1 to 3. We ran it with a ratio of 0.34 to 0.98, which is not the same as the 1 to 3. So therefore, one of them will run out first. Does that kind of hit on that topic for you okay?
Yes, thank you.
Awesome. I'm reading in the chat, trying to catch up there. Where did the halves come from? Yeah, so that was back up here. The definition of making ammonia had us required us to make sure we had a 1 in front of that coefficient of ammonia, because this says per mole. So I know that that has to be 1 mole of ammonia. And all I did then was use fractions to balance the equation to keep it at a 1. And we said, oh, you know what? If that bothers you, you can put whole numbers in here, but make sure that whatever you did to those coefficients, you do the same thing to your delta H.
I have a question.
Perfect. Yeah.
So
Go ahead.
So I didn't do the problem the same way you did with the fractions. Instead, I did it with the whole numbers because that's what makes me the most comfortable because the fractions can be confusing. And what I did
Okay.
was I found the how many moles of N2 would be in the NH3, and I found how many moles of H2 would also be in the NH3. And then what I did was I just multiplied it times the coefficient of the 2 moles of the two that I put in front of the NH3. And then I compare the moles of NH3 from both of I compared the I'm trying to
No,
explain it, I'm sorry.
yeah, but I think I hear, and again, when I mentioned there are so many correct ways, all that matters is that your units cancel throughout. But what I think I hear you saying is you're doing a mole-mole comparison to ammonia from each reactant to determine your limiting reagent. That's a beautiful approach as well. Whatever works for you to determine which one runs out first. You have to determine the limiting reagent to determine the KJs. Once you do that in whatever way makes sense, you're golden. For me, I always said the guaranteed way not to make a mistake is to solve two separate problems and just circle the smaller answer. Because one of the most common mistakes I see for beginning chemistry students, especially Gen Chem 1, when we take our limiting reagents and just to kind of show, they look at these numbers, they both to moles and look at those numbers and go, oh, this is bigger, this is smaller, therefore the smallest one must be the limiting reagent. And that's wrong unless it's a 1-to-1 ratio, but this isn't, right? So I like what I'm hearing. You're saying what must be the moles of ammonia from each, and then you're determining the limiting reagent from there. It's a
Right.
perfect approach.
But the only thing was, I was just wondering if it was correct because you said that if we put the coefficient of 2 in front of the NH3, that we have to multiply it times 2. And I didn't do that when I did the mole to mole comparison after multiplying. I didn't put the coefficient of 2 when I multiplied the least amount of moles times the kilojoules. I didn't put a coefficient. I didn't multiply it.
Okay, well, make yourself a note, practice that with it. Yeah, that you want to make sure your approach is leading you to this answer. You know, once you solve for your limiting reagent, however you get there, there's only one right answer to the question. How many kJs? Well, it's negative 29.4 based on the number coming from the limiting reagent. Okay. All right, well, let's go on and kind of look at the next example and see if we can generate more conversation. Now, this question looks overwhelming at first, but what it is the multiple choice. It's not part of the work. And the reason I wanted to snapshot the multiple choice is to kind of talk about distractors and how I can quickly eliminate things as I'm working through a test. All righty. So here the question asks me, which one of the following chemical equations corresponds to the standard molar enthalpy of formation of sodium chromate in its solid phase? So I picked this one on purpose to put next, because again, I get to emphasize the vocabulary term standard molar enthalpy. And what that means is how much energy is needed to make 1 mole of the compound from its elements in their natural state. Right off the bat, there are some choices here that I can just eliminate because I see that they're not elements in their natural state pointing at the compound. Here's a for example. Look at letter B here. This is not an element, it's a compound. Well, that's not the correct definition. They have to be elements in the natural state pointing at the compound. And I can get rid of choice D from that very same reason. These aren't elements, they're compounds. What we need to do is to point at the compound from its elements in their natural state. What do you think about letter A? Do we see anything upsetting about elements in their natural state that could choose us to just kind of toss it out? I noticed, perhaps you do too, sodium carrying a subscript of a 2, but the oxygen not carrying the subscript of 2. In nature, elemental sodium is just an atom. In nature, oxygen is a diatomic molecule. So based on those subscripts, I can get rid of choice A. And the same thing is true down here in letter C, isn't it? Oxygen in its natural state is not an atom, but it's a diatomic molecule. Based on that, I can eliminate choice C. And I come down to the very last equation. Sodium as an element in its natural state is a solid. Carbon as an element in its natural state written as a solid. Here's diatomic oxygen written in the gaseous state. All of these are elements that are found in nature, the way that they're written. And so I look at this question and think of it as really a process of elimination, getting rid of choices for just for the equation that doesn't meet the definition of standard molar enthalpy. Last equation has every element written in its natural state, pointing at the compound, and it's 1 mole of the compound. Let me give you a moment to process, see if you have a question on this one. Would you have gotten this one if it were on your test? I'm circling back just a quick moment to this question I see in the chat. It says, what's a faster way of finding coefficients that balances out the equation, especially the fraction ones? I don't know if I have a trick about fast balancing other than a ton of repetition, but I can emphasize, just to circle back where we started our last problem to address that chat question. The definition said enthalpy of formation. That means 1 mole of compound. And so I know I have to have a 1 in front of the ammonia. What can I multiply by 2, make it become a 1? That's why I said 1/2. 1/2 times 2 is 1. I have 3 hydrogens on the right. When I multiply 3/2 by 2, I get 3 hydrogens on the right. So that's how I got the fractions over there. So I have 1 nitrogen on the right, 3 hydrogens on the right, and on the left, using fractions, I now balance the equation that way. And I don't see a chat question on this guy. Anything before we move on? Super cool. All right, friends, let's take a peek here. Here's, and again, I know I'm emphasizing heats of formation, but it seems to be traditionally a place where we commonly trip. So I'm kind of emphasizing 3 in a row with this definition. This is just a quick thought question. In the reaction below, the delta H of F, that means the heat of formation. How much energy does it take to build a compound from its elements? Which one of these would be assigned a 0? So again, I'm emphasizing the heat of formation for compounds have values. Since we use elements to build compounds, elements themselves that are in their natural state, by the very definition of delta H formation, are assigned a 0. When you look at this equation, this guy here the only element in its natural state. Therefore, out of all those choices, the delta H of formation is assigned a 0. So that question can be kind of intimidating at first, but all you do is look through all of the ingredients to say, I'm just looking for an element written as we find it in nature, and I can toss out choices that are compounds very quickly. Move to process, put your question in the chat. I think I've done 3 in a row on this, so I might remember it's pretty good.
So for things like this, you look just strictly for the elements instead of the compounds, just like the one before.
Yes.
For the heat of
The
formation.
delta H of formation is 0. That's the key here, 0. Any element in its natural state is always 0. And yes, I'm going to send the recording link out to the entire class for those who come. I see that in the chat. Take a peek at a next one, and I kind of steering now into just basic unit conversions. I really think a lot of the chapter can be all accomplished with just understanding a little bit of dimensional analysis, how to cancel units from what we want, from what we were given. And here's one where I picked a unit conversion. And it's, again, I know why it's a most missed common question. Let's read it together. It says, the specific heat of bromine liquid is 0.226 joules per gram Kelvin. Molar heat capacity, which would be then in joules per mole Kelvin, is, and then you would have, the list of A, B, C, D, E. So what we really are thinking about is starting with 0.226 joules per gram Kelvin. And really what we want to have for unit is I didn't mean that. Let me erase that. We want a joule and then the line per mole Kelvin. So we want to really just convert from specific heat in grams on the bottom to a mole unit on the bottom. Alrighty. The reason I selected this is I know that with confidence we can convert grams to moles, but with bromine, the reason I believe this one is most often missed is we forget that bromine is one of those lucky 7 diatomic molecules that in nature it's not just Br, but it's Br2. And therefore the molar mass of bromine is 160 grams per mole. Bromine is approximately, well, it's 79.9 from memory, but I'm going to just round a little bit, especially, friends, if it's multiple choice. Rounding a little bit on that last decimal is going to lead you to the correct answer. So don't waste a ton of time carrying so many decimals for multiple choice questions. So if it says we have 0.226 gram or joules per gram Kelvin, we want to convert that into mole Kelvin on the bottom. The trick here was remembering that diatomic molecules have to be used with doubling the molar mass. All right, so here we have 0.226 joules per gram Kelvin times, and we just said there is 160 grams in 1 mole, and that's all this took to cancel grams and leave us with what we desired, a joule per mole Kelvin. There's Kelvin over here. So this was as simple as 0.226 times 160. I picked this problem 2 reasons, really. Emphasize that if you're reading a quiz question and you're stuck, not really sure how to proceed, just look at the units. What units are you given and what are you being asked to convert them to? Oftentimes you can see a pathway by thinking about unit conversion. And then I got to remember bromine. If I'm going to make a mistake, I might forget bromine is Br2 and not just Br. Do you remember that little sentence? Or maybe you weren't ever. I always thought horses need oats and for, so that's your fluorine, for clear brown eyes. Those are your 7 diatomic molecules off the periodic table. Horses need oats for clear brown eyes. So when you read bromine or any of those other 7, remember the molar mass would be double for a molecule. Give you a moment to think before we move on. Ask a question if it's in your head.
So those diatomic elements are very important for when we need to double the molar mass of before we start our conversions, correct?
Correct. And you know what? I would suggest they're important in another situation too, and that's when, a moment ago when we were trying to find the molar, if I think about, just let me clear the ink off of this for a minute. If we look at this question fresh, I think it's important to remember the 7 diatomic molecules in a like this one again too, because if I didn't remember that oxygen in nature is diatomic, I might be fooled into thinking that that's an okay equation. And here it is again. If I didn't remember that oxygen is one of the 7 diatomics, I might be fooled into thinking that's a good equation. And the other part is remembering that there's only 7 molecules, which helps me eliminate this guy because Na2 is not the way we find it in nature because it's not one of those lucky 7 elements. So not only at the process of finding molar mass, but in kind of looking at those equations for heats of formation, I can think of those 2 places where it would be important to remember those 7. Good question. Anything else on your mind, my friends?
Hi, what's the saying again for the diatomic elements?
The sentence?
The saying you had, yes.
I read it as horses need oats for clear brown eyes. The eyes are just the eye. I think there's quite a few mnemonic devices that help remember, but that's the one that sticks in my head.
Could we go over like a heat of reaction problem? Because
So,
I was wondering, I'm sorry, if like, so you know how for CO2 it is negative 393.5 kilojoules. Are we gonna have that paper that had like all those
yeah.
what you call it?
So the
I forget
thermodynamic properties.
Yeah.
You know what? Here would be a good example. So the answer is yes, you'll have them, but you don't have to look them up on a table. You don't have to have your own separate document with the formation, with the appendix, so I call it. And I know in Alex, you could just click and it would appear, but in the quiz or the test bank, the problems will always provide you the delta H information right in the problem. So you don't have to go externally and look them up. And I can kind of show you in a few different ways. You know, here's one I think you might be referring to is, I got to go in and do some calculations, but I have to know the delta H of those things. Notice how a data table is provided for you right in the question. Or at the end of each equation, you'll see them provided for you right there. So they're not go fetch them and bring them back, but they're going to be right in front of you for each question.
Okay, because I was so confused. I was like, where are these numbers coming from if I don't have access to them? Okay. I think that cleared up a lot
Sure.
of words
There's
for me.
no way you would know those by heart. No way. You know, for me, when I was working problems in my instructional lessons, I had my appendix just out from the textbook, you know, and I could just look them up. Or if you're working, like I said, in Alex, they have a little click and you find it right away. But with quizzes, we want you to be efficient with time. So you just kind of put them right in the problem for you. So at this point, I can definitely ask what we want to work on next. I have some Hess's laws, or I have what you just mentioned, enthalpy of reactions, where we can look at those products minus reactants. Also, just some simple calorimetry problems. Where would the class like to go next? Do you have a topic?
I actually do. I would like to know how more information on when we're like given three of those three equations with the delta H, and then we're given a target equation. I would like to
Okay.
more information on how to solve those.
Perfect. That happens to be the slide. It's called Hess's law. And you hit the nail right on the head when you said we're given these elementary reactions and then a target equation to build. So this is what it would look like on the quiz. You're given the following reactions, and then I can see, you know, two elementary reactions and their delta H. Underneath it, it says, okay, now I've got to use those two equations and somehow add them together to create this target. So it's, I always said, it's just a little bit like a jigsaw where you've got to put the pieces together and build a larger structure, okay? So here's my strategy. With most problems, there's multiple correct ways to start, but this is how my brain works. I'm just going to kind of think out loud. My mind says, oh, go ahead.
What are those question marks? What are those supposed
Oh,
to be?
thank you. That when I copied and pasted, it didn't come through. Those are indeed the arrows in that reaction. Thank you. The only formatting issue, sometimes the subscripts don't come through when I copy paste just right, but we get the idea. And again, when I just lift off of a Word document and import to my notebook here, it sometimes misformats. But that's the arrow separating left and right. So as I was just getting out loud thinking, for no other reason than it's written first, I always look at the first reactant in the target equation. That's where my eyes go. And I see that it's 3 units of Fe2O3. What I then do is go up into these elementary reactions and see if I can locate, where is it? And where do we find Fe2O3? Well, here's what I like. I can see it in the first equation, like it's on the left-hand side because that's where I want it to be. But what do we need to change about it? In my elementary reaction, I only have 1 mole of it, but in my target equation, I need to have 3 moles. So So what I suspect, this is just my, intuition, is that with this first reaction, I'm going to need to distribute a 3 through the entire thing. And when I would do that, I would triple the delta H. And again, repeating my Y, the target equation has 3 in front of the Fe2O3. Up in this elementary reaction, I only have 1 of them. So I'm going to need to distribute a 3. And friends, one other thing I should say is it's the only place that I see Fe2O3. That's why it's so interesting to me. And I say that because if I come down and I look here, the reactant is CO in my target equation. But I see carbon monoxide in both elementary reactions. So I don't think it's very helpful at all to figure out what to do, especially with the second equation, because it's appearing in both. And I can say that also with, you notice how the CO2 appears next here, but it's appearing in both elementary reactions. So I think it's helpful to study that one and try to figure out what to do with those elementary reactions. The key is to find unique places to give you insight into what to do with the elementary reactions. So I liked starting with this Fe2O3 because it was uniquely here. My eyes would then go to the Fe3O4 because it's uniquely here. And it lets me know what to do with that second reaction. Again, I like the side that it's on. It's on the correct side as a product. My target has a 2, but over here it's just at a 1. So I would suspect that we have to double all of the coefficients through that second reaction. And when we would do that, we would need to double the enthalpy as well. Whatever the coefficient is that you distribute through that equation, make sure you do the same thing with your delta H. Now we can prove this to ourselves. I'm going to rewrite equation 1, but by distributing a 3. So I have 3 units of Fe2O3 plus 3 times 3 is 9 carbon monoxides. 3 times 2 is 6 Fe's. And 3 times 3 is 9 CO2s. And of course, delta H be 3 times negative 28. I'm going to rewrite my second equation, but when I do so, I'm going to distribute a 2. So 2 times 3 is 6 Fe's plus 2 times 4 is 8 carbon dioxides. Pointing now, 2 times 4 is 8 COs. And 2 times 1 is 2 Fe3O4. And what can we simplify if we were to add these equations together? In other words, if something appears on the right side of one equation, it can simplify out with something on the left side of the other. So for instance, I notice on the left side here, there's 8 units of CO2, but on the right side here, there's 9 units of CO2. The remainder would be 1 unit of carbon dioxide on the right. 6 irons, cancel that out completely. Here we have 8 units of CO with 9 units of CO on opposite sides of the arrow. When I simplify, that would leave me a remainder of 1 on the left side. And of course, 3 units of Fe2O3 remain up on the top one, and 2 units of Fe3O4 remain on the bottom one. So if I'm using the quiz, I probably wouldn't write all this out because we're trying to be efficient. But I just wanted to prove it to you that we added those 2 equations, and indeed, this was exactly the target that we tried to make. So what's left to do is to add those 2 equations enthalpy together. We have to add 3 times negative 28 plus 2 times 12.5. And that gives us the heat of reaction for our target equation.
So is this method the same even when we're given 3 of those elementary equations to start off with a target?
Absolutely, yes. Interesting. I'm negative 59. I'm just trying to write that before if anyone else double checked my math, I didn't. But to answer that is, no matter how many elementary reactions are given, your job is to use them to build the target. But I actually love that you asked me that question, because if I may go to the next slide, is everyone ready? He wrote, be sure your answer is a unit symbol if necessary and round to the proper sig figs. Absolutely, thank you. So again, this should have a decimal with it. My screen, I didn't carry it. So I'll emphasize the quiz and test bank level. Your choices in multiple choice will not be so close to say, like, is it 59.01 or is it 59.0 or is it just 59? You're going to find an answer that you can select with confidence because the other choices are not that close to it, just to kind of help. Whereas Alex is very picky about sig figs. Absolutely. To kind of clarify about what you were just asking me related to Hess's law, I did this one on purpose, and we can just kind of talk about it. Here, this is again a Hess's law, and I'm given 4 equations to create this target. Calcium carbonate decomposes out comes calcium oxide and carbon dioxide. Before we get so overwhelmed about how am I going to add 4 equations together and get them all simplifying, I wanted to discuss distractors. Because I'm given 4 equations doesn't mean that you have to use all 4 equations. So in other words, even though the list might be 4, you could go in and just pick and choose the equations that you need to build the target. I'm going to give you an idea here that when I look at calcium carbonate, CaO, and CO2, those are the 3 things that I need to get from the equations below. Ready? My eyes go right here to this equation. Carbon plus oxygen give me carbon dioxide. In any of these other equations, I do not find carbon, or, I do see oxygen there, but let me focus on this guy then, the carbon. Do you see anywhere else where carbon is written in those elementary reactions? Is not part of this equation. There's no C anywhere. So I would have to be able to cancel that out in order to use that equation. And there's no way to cancel it because it doesn't appear anywhere else in the other equations. Same could be this argument here. This Ca, it's not part of the target equation, and I don't see the element calcium appearing anywhere else in the elementary reactions. Therefore, it would be impossible to cancel it. So I bring this up because even though there's 4 equations, don't feel like you have to use all 4. It's kind of like a trick in the test bank where you feel like you have to use everything that's given to you, but you don't. I'd imagine that we could build this target equation just from the first 2 equations and never even use equation 3 and 4. So I wanted to throw that out there as a reminder that sometimes the list of the equations is much more lengthy than you actually end up needing to create the target. So my strategy, again, just kind of talking out loud, let me clear the ink from the page and we'll start over. For no other reason than it's written first, I look at the first reactant in the target equation. I go down into the elementary reactions and I see where I find it. I find it in the second equation and only in the second equation. But I think about, we got to flip the direction because it's on the wrong side of the arrow, but I have the good number, 1 mole of it. So I'm just going to say we're going to need to reverse equation 2. And when I do that, I know that I got to make this positive. In terms of the CaO, I go there next because it's just written next. And I've already decided to toss these 2 out because I can't eliminate the carbon or the calcium because they don't appear anywhere else. CaO, I have the correct number and the correct side of the arrow, so I think we should just leave it alone. And sure enough, if I write the first equation over just as it's written, and I reverse the order of the second equation, we can then cancel calcium hydroxides. We can cancel the waters. We've created CaCO3 pointing to CaO and CO2. And we never needed equation 3 or 4 to build it. All that we left to do is to say, we'll take equation number 1, 65.2, and we're going to add it now to a positive 113.8 because we reversed the direction of equation 2, so we had to flip the sign. And all we'll be left to do is to sum those 2 to find our final answer. Yes. You just use reaction 1 and 2 and use all of the equations provided. I just want to emphasize that that's okay. Just because a problem gives you 4 or 5 equations doesn't mean you have to use them all.
So when a problem gives us 4 or 3 equations below, a simple way that we can use it is by looking at the compounds in the target equation and seeing if they match up with one of the compounds in the elementary equations. And then if they don't have those compounds, we can just simply eliminate them altogether.
Yes. Yeah, the whole theme. And you hit it right there. Is that's exactly what you're asked to do. And you know, my strategy is to focus on the first reactant, go find it, then go to the next reactant, go find it. But remember too, if it's appearing in more than one place, kind of disregard it for now and go find something unique that helps you know what to do. Beautiful. So I see in the chat, what about this for the target equation? Well, I never looked at it because it already was present. When I had this reaction from number 2, I flipped the direction. It brought me the carbon dioxide already. So I didn't need to consider it further because I had it on the correct side and I had the correct number. So I kind of just left it alone. It was perfect already. Nope. That's a good question. You'll never use the same equation twice. You'll use it just once. And then the other part of it is you don't have to use every equation provided, but if you use an equation, you'll use it just once. Cool. How about, this was emailed to me by a few people, a problem something like this one. Let me just move my chat over there. Given the data in the table below, calculate the delta H of reaction. And I'm given PCl3, and I'm just going to put the number right underneath it, 288.07. Oops, forgot my negative. Negative 288.07. HCl is negative 92.30. Only other one is the pH3 is given as 5.40. Why don't we get a number for chlorine? Yep. That's right, Colin.
Because
Good
it's
on
in
you.
its natural. Oh, sorry.
No, I read it in the chat. I'm sorry if I overspoke someone. I apologize, but you're absolutely on target. We don't need it, do we? It's a 0. So element in its natural state, you'll not be given the thermodynamic data because you're expected to remember it's just 0. So sometimes we get a little nervous that, oh my goodness, there's 4 ingredients, but only 3 data points. Well, that's because one of those ingredients is an element in its natural state. Otherwise, you must have that provided because you're not expected to know it by heart. So you would know that this delta H of reaction would be the sum of the products, which would be 3 times 0 plus 1 times 5.40 minus negative 288.07 plus 3 times negative 92.30. And you can simplify from there, but the only purpose was to remind you that data tables will be provided for you in the quizzes or the tests, so you don't have to have your own chart out. You don't have to go looking for it in another section. And if you only see 3 of 4 ingredients, that's because the other one's a 0. This is called think time. Let you take a moment and digest, see if something pops to mind.
So if I'm sorry, what were you saying?
Oh, I apologize. I was just processing the chat. Are there any really complicated problems in the bank with many steps similar to a few on the Alex homework? I'll be brutally honest. I've heard from other students, in previous terms that the Alex is a bit more demanding than the quiz bank is. That once you come off of Alex and have mastered all of those, you are well primed for success on the quiz because I think you've worked enough problems that are complicated that sometimes you get scared that these look easy. And that's okay. They really might be just easier. I think of an example on the Alex where 2 homework questions had you calculate the enthalpy of a reaction where Q wasn't exactly the same thing as H, and you had to alter that. And there's not like that in the quiz. I know that. So things like that. Yes. So that's what I've been hearing, is that you are well prepped to think the quiz is much more manageable after coming off of the Alex, where it really was demanding. Then else ask a question. I cut him off. I apologize. We've been going an hour. Is there any other topic you wanted to discuss before we were to another?
Have you done a enthalpy change problem yet? Have we done one of those?
So do you mean enthalpy change of a reaction, or like calorimetry, or, because that's a pretty broad question. Let me give you I have I could do an ice cube problem. That's calorimetry. I could do heat capacity. I could do, I haven't worked many calorimetry problems. When you say enthalpy of reaction,
Yeah, like an enthalpy of reaction. Yeah.
maybe something like this one. I think if I have, I have quite a few kind of pulled, and I want to pick the one that can you show another one similar to the first one? Enthalpy of reaction is so broad. I want to make sure I pick up. It would be the enthalpy of reaction, the one we first started, or I know we went over Hess's law. This to me is another one of enthalpy of reaction. So I'm kind of just so confused maybe about what I could best show you. This looks good?
Yeah. Yeah, like this one or the one before, those looked good. Those ones got me.
Okay. Well, let's take a peek at this one since we're staring at it.
Cool.
This one talks about combustion of butane, which brings you to your discussion topic this week, right? When you take a hydrocarbon, which is a fuel, and you combust it, a ton of heat energy comes out, right? So this is butane's combustion reaction. And I want to emphasize that there's a coefficient of 1 here, and to balance it, we're using a fraction in front of the oxygen. And that's okay, because by definition, the heat of reaction is going to be per 1 mole of the fuel. What is the enthalpy change following reaction? So really what this is kind of a trick on Hess's law, being asked, how can I turn this first reaction into this target equation? So it's as simple as thinking of this as saying, I have one elementary reaction that somehow I have to turn it into a target equation. What is it that we could do? And it ends up to be kind of an easier problem when you approach it from that strategy. So out loud thinking, for no other reason than it's written first, in my target equation, I look at the first reactant, it's carbon dioxide. Go into the original equation and see what we would need to do to create 8 units of CO2 on the left side instead of 4 units on the right side.
Okay. So multiply by 2.
So would you flip
it? Yes, beautiful. Yeah, that's it. You're going to flip the direction and you're going to multiply it by 2. So what does that mean to the negative 2877 kJs? When you flip the direction, the negative becomes positive, And when you multiplied it through by 2, you will
Multiply that by
double. Beautiful. That's exactly right. So positive 2877 doubled is your reaction. See how simple they can become when you approach it from the Hess's law. What do I got to do this side to make it turn into this guy? Yeah.
Yeah, I think the trickiest thing is just determining like what to use for the problem.
Right.
But
I agree.
that makes sense. So
Yay. So here's hoping that one shows up for you. The calorimetry, I think most people are saying that's going well. So this one is a bit interesting as well. You want to stay a minute, or do you, those who can stay? I know I'm just giving you a minute to kind of read through it. Here we have N2H4 combusts O2, giving us N2 plus 2 H2Os. Here's given 6.50 grams of our fuel, N2H4, and what happens is that it combusts and releases, evolves, tells me that it's heat releasing, so negative 126.2 kilojoules. So when you think about what is it that they're asking me, I was given a gram of N2H4 and tells me when it combusts, this is the heat that came out. When you read what you're being asked for, enthalpy change per mole, that tells me what I want to solve for is a kJ per mole. I want to turn my into this wanted unit. So really what it's saying is when 6.5 grams what's that? 12, 24, 28, 23, 132. Is that molar mass? I better double check. 28 plus 4. Looks like 32 is this molar mass. So 1 mole over 32 grams. I'm just converting my grams into moles. And that's 0.203. So think about what we just said. If negative 126.2 kilojoules was released when 6.5 grams of fuel was combusted, that's exactly what we were told in a kJ per gram. We said that instead of having grams down there, what did we really want? We wanted to have kJ per mole. So another way of writing that is negative 126.2 kilojoules of heat combusted, released, was evolved when 0.203 moles combusted. Let's simplify that. Negative 126.2 divided by our mole number of 0.203, negative 621 point, and I'll just round. That's all there was to that problem. And it's really a good question because it's not complicated if you just think about units. This many kJs or this many grams, okay, but I really wanted to be kJ per mole. And so we just manipulated units to turn it out that way. What do you think?
that does make it easier.
Yeah. It's easy watching someone else, right?
Yeah, that's true.
Yeah.
I have a question.
Sure.
Okay, so the problem that I've had a question with, I'm just gonna read it because I wrote it down from the quiz when I got it wrong.
Okay.
It says the value of delta H for the reaction below is, and then it gives whatever kilojoule it is, and it says calculate the heat released from the reaction if however many grams of whatever element they provide, and then it gives the equation. I know how to solve it now, but I just want to kind of go over it.
Yeah. So without seeing the problem, it's so vague. So if you give me a minute, I can pull up your quiz and see if I can screenshot it. Ash. Have you taken multiple attempts on your quiz yet, Ashley?
Yeah, I've taken two.
So if I were to pull up attempt 1 or attempt 2, which one would I find it in? Do you remember?
Maybe attempt 2.
Okay, I'll pull that up and I have it right in front of me and see if I can find that question or one similar. Well, all my equation pages come in the middle. That's no. Here's one that looks like a Hess's law that gives you 3 target equations. No, and actually, what's funny is you have one very similar to this one that we talked about here. So that can be strategized. But that's the only really on your quiz that you missed was the, do products minus reactants, or maybe I should look at your first attempt. We worked the one for ammonia. That one was done. See a Hess's law. Another Hess's law. Oh, I'm sorry, I'm not finding one.
I think it was like towards the bottom. It said the value of H for the reaction below is like negative 186 kilojoules. Calculate the heat in kilojoules released from the reaction of 25 grams of CO2.
Similar. Let me see if this is enough similar. Here's an equation. CH4 is going to react with 3 units of Cl2, and I'm going to point at CHCl3 plus 3 HCl's, and it says delta H for this reaction is given as negative 336 kJs. Then it says, given 23 grams of HCl, tell me how many kilojoules of heat are released. Yeah, so this actually is nothing more than a stoichiometry problem. So what we know from the balanced equation, that the HCl is right here, that when 3 moles of HCl are produced, this many kJs of heat are released. So think of it as nothing more than a stoichiometry problem. I'm starting with 23 grams of HCl. Coefficients stand for moles, so I want to change my grams to moles. So my first conversion, in 1 mole of HCl, there would be 36.5 grams. That's me just adding an H and a Cl's molar mass. And then we have our stoichiometric ratio, what we want over given And I'll just make sure that you know that I'm pulling this from the equation. We want kJs. From the balanced equation, it's negative 336 kilojoules. And from the equation, the coefficient in front of HCl was a 3. Want over given. So notice that in step 1, our grams of HCl canceled. In step 2, your moles of HCl canceled, and you're left with kJs. So I would hit that on my calculator going 23 divided by 36.5 times negative 336 divided by 3. And someone can check me. Negative 70.57, I'll say 6.
So you just gave yourself the 23 though, right? Like you didn't get that from anything on there?
Oh, I only got it from reading a sample problem from Ashley's quiz that she had taken. So
Okay,
just to kind of
okay.
share, I have another computer set up, yeah, and that's where I
Okay,
pulled. So
gotcha.
I just went over that direction and pulled up her quiz just to give me a
Cool.
sample problem. Yeah,
Makes sense.
a
Yeah,
ton of hard work today. Good on you guys.
I have a question also
Meeting
regarding
last-
that we're taking
Go ahead.
on Sunday. Is the test timed as well? Because a lot of these problems, they seem like really lengthy to do. So I was just more concerned with the time restraint versus that, because I know a lot of times when I'm taking a test and I have a time test, it kind of gives me anxiety to make me want to rush to choose whatever the right question is, which is probably why I got like a couple wrong on my my quiz, because it was timed to be 45 minutes. And I feel like a lot of these questions, like you need like a substantial amount of time to do them and check them and make sure they're right in order that we like have success on our
I
exam.
completely hear you. And yes, to work 10 questions in 45 minutes, but not all of them are computational. So I hear you that you are timed, but it's so difficult because I have to balance so much time that students have an opportunity, and it just leads to, not that I'm saying anyone in this room would, but using some help, outside help. The more time you have to go look things up on an outside Chegg source or something, balanced with a realistic time to complete and actually work problems. I do this very statistically. When I look at the quiz with 45 minutes, over 95% of the students submit with time left. And so that's an indicator to me that that's ample time, that they didn't use all their time. And the same with the test. The tests are timed as well, but they're longer. You know that, that they're timed for, let me look for you. Anybody know?
No, not yet.
Yeah, right, you haven't looked. So these are timed restrictions, 25. Oh, hour and a half. So you have 90 minutes to do the test. And again, when I look back just historically, the overwhelming majority of students submit their test with minutes left. Now, if you personally have test anxiety and are struggling with minutes, that's a conversation you and I should have alone. And we can certainly do that. But I have to balance getting it done without having enough time to go cheat and look them up. Does that make sense? It's just this whole online stuff. It's a balancing act of not allowing so much time that I can. You'd be surprised how many hire tutors to just look at their quiz and take it for them, so that's the reason of timing it.
I understand that. I just thought that would be able to suggest it because we are recorded with the webcam. So I just thought it would just.
Right. And again, 45 minutes has proven to be ample time. And certainly the 90 minutes, hour and a half has been proven to be ample time, overwhelmingly ample time for students to submit. But I will encourage you to say, if you're suffering from test anxiety, it's a private conversation for you and I. If your minutes aren't ample, because I'm not going to, for one person, I'm not going to change everyone else's time limit. So I hope that makes sense. But, there's the real thing. I get it. Test anxiety is real. Like you see a clock ticking. Sometimes that's the opposite of helpful, for sure.
Have you had people cheat on Lockdown Browser? Like, I'm curious because I just feel like I don't even know how you do it.
Yeah. So here, let me show you all the ways. Yeah. The answer is yes.
Don't do it, you know?
Yeah. Surprisingly, they're not smart about it, or maybe they're so smart they don't know what they're doing. But the ones who have gotten caught have not been doing it smart. And so, yes,
Yeah,
it does
'cause,
happen.
Like, I'll be on there, and like when I was taking the quiz, I didn't print out the charts or anything, so like I had to pull out my phone and I showed it up to the camera, and I was like, I'm just showing you my chart right here, like, because this is what I need to use. But
Okay,
like,
that's
what can I do
interesting
in that?
because not only myself, but our LAs through the recordings, and you get red flags anytime you do something suspicious. And so when we look at a recording, it's not like we're watching you live for the whole time. But what happens is it creates little segments that are of interest to you to look at. That's all.
Gotcha. Okay.
Yeah. So one of the most common ways you get flagged actually is having somebody inadvertently walk behind you. You live in a house and somebody walks by, you can't help it. And that gets flagged and we see what happened and we go on, But another interesting thing is, no, because I have it set to where you're supposed to be writing practice problems. You're supposed to be working on your desk in front of you. So that's not flagged. What is flagged is if you're looking off to the side for too long. That gets flagged. So
yeah, because I was like looking down for a while and it was like, oh, you're not in the camera anymore. Like, and I was like, oh crap,
Oh, your whole head disappears. Yeah, that gets flagged. Not just looking down, but again, those are very quick to see that you're just working. It's if you see somebody holding, just in their camera, you can, you're looking up at a different screen that's been caught, people who have stuff written on the whiteboard behind them, something like that, so.
Yeah. Oh, okay. Thank you.
Oh, here's a question. Are the test-taking tools available on the quizzes and exam? Correct. Yes, they do appear in the exam, but I'd also encourage you, if you prefer, to just print a clean copy for test-taking days. Then you don't have to keep scrolling up and down to find them all the time. So if you choose to, they're absolutely provided on every quiz, but that means you have to scroll up and down and go back to them. So if you want to just be more efficient, just have a clean copy of those tool pages on your desk. And you can see that there's many of them, and you don't really need all of them for the first test. So you might just want to have a few of them out in handy. Your periodic table, but you don't need your kinetics formulas and all that stuff, but they're all there.
Okay.
I wrote a note with the H2N2O2. I don't know what that note would be. So I'm trying to read through the chat. Somebody asked me a question about H2N2O2. What was it that you wrote?
It was just a quick reminder of like a shortcut way of remembering that the delta H equals 0 for all those 7.
Needles thing. I gotcha. Oh yeah, that's fine. Yeah.
Okay.
I was like, what word is that? Oh my God. Good. Well, good luck on your quizzes and use those, as I say, to practice, get as many practice problems in, work for proficiency, work for speed so that you can celebrate your learning come Sunday and have a great outcome. Any last
thanks for the
questions
help.
before we get going? Oh, my pleasure. Yes, absolutely.
Thank you so much.
Good, good. I'm glad you found it valuable. Absolutely. We'll make a date again for prior to the next time.
I
Yeah,
like to
definitely.
have a meeting with you after this, I guess, to talk about my test anxiety.
Yeah.
Ashley, who said that?
Yes.
Okay, Ashley, I'll just hang on the line and we'll just wait for everyone else to hang up. Bye, everybody. Ashley, I'm going to stop recording though, because this will be a private conversation.